Welcome to the Deep Dive. We cut through the noise to bring you the essential insights. Today, we're jumping into something really vital and, well, pretty complex. How deep learning is shaking up prognostics and health management. Think of this as your shortcut to understanding the future of keeping complex systems running.
Yeah, it's fascinating stuff. What's really grabbed me is how this cutting-edge AI, deep learning specifically, is being used to, well, keep things running smoothly and even predict failures before they actually happen. We're moving beyond just fixing things after they break.
Okay, right. Let's unpack that a bit. Prognostics and Health Management.phm. It's fundamentally about optimizing how we maintain complex industrial assets. So we're talking about ensuring high availability for really critical things, like trains or aircraft fleets. And that involves spotting early signs of trouble, diagnosing the cause, predicting how much useful life is left, all while trying to keep the costs manageable, of course.
Exactly. And historically, PHM, it faced this huge challenge, the sheer amount and, frankly, the messiness of sensor data. You've got temperature, vibration readings, images maybe, just streams and streams of it, heterogeneous data. And traditionally, getting useful info out of that, it meant really intensive manual feature engineering, which was, well, it was time-consuming. You needed domain experts, and it often struggled to generalize across different situations. You'd end up with missed alarms or false alarms because those handcrafted features just couldn't catch everything. A real bottleneck.
Right, that makes sense. So if that manual feature engineering was the big hurdle, how does deep learning step in? What sparked its rise for PHM?
Well, the deep learning explosion itself came from a few key things converging. Suddenly, we had access to massive data sets, plus big breakthroughs in the algorithms themselves, and crucially, hardware got much cheaper and much faster. But the real game changer for PHM, it's deep learning's ability to basically skip that painstaking manual feature stuff. It learns directly from the raw data. Its power is in automatically crunching huge amounts of this condition monitoring data, pulling out useful patterns from, really high-dimensional sources, and understanding complex relationships, both functional and over time. It helps automate building the models, makes them more robust.
Okay, so it gets its hands dirty with the raw data automatically.
Yeah.
Let's talk specifics. Where is this making a real difference? Because theory is one thing, but I saw mentions of things like natural language processing, NLP,
Yeah.
using AI that understands language on maintenance reports. That sounds wild.
It does, but it works. Analyzing that free-form text in maintenance logs to spot subtle clues about fault causes that engineers might write down.
Oh.
Or think about computer vision. Using things like deep convolutional neural networks, CNNs, the AI, good at seeing patterns in images. They can automate inspecting railway tracks for tiny cracks, for example, or meticulously scan, say, jet engine parts using borescope images. Much faster, potentially more consistent.
So it's not just numbers, it's text and images too.
Absolutely. And for the number streams, the time series data. Supervised learning with things like recurrent neural networks, LSTMs, are particularly good there. They're designed to understand sequences like sensor readings changing over time, temperature fluctuations, vibration patterns, really rich data for prediction.
Right, sequences over time.
And critically, because in the real world, you often don't have tons of perfectly labeled fault data. Unsupervised and semi-supervised learning methods become absolutely essential. They help models learn even when the data isn't perfectly neat and tidy.
Okay, that makes sense. So looking forward then, where is this heading? What are the sort of cutting-edge directions?
We're seeing some really promising stuff. Transfer learning is a big one.
Transfer learning.
Yeah, the idea is you train a model on one machine or one set of conditions and then adapt it to work across a whole fleet, maybe even with slightly different sensors. Huge potential there.
Right, instead of starting from scratch every time.
Exactly. Then you have things like deep generative algorithms. These can actually create synthetic artificial fault data.
To supplement the real stuff that's hard to get.
Precisely. Helps train more robust models when real fault examples are scarce. And another exciting area is physics-induced machine learning. Trying to bake actual domain knowledge, the physics of how things fail, directly into the AI models themselves, make them smarter, maybe more interpretable.
That sounds powerful, but it also sounds like there might still be challenges, hurdles to overcome.
Oh, definitely. While the potential is huge, better availability, safety, lower costs, there are significant hurdles.
Yeah.
Interpretability is a big one. These deep learning models can be like black boxes. We need domain experts to be able to understand why a prediction is being made, to trust it.
Yeah, I can see that being crucial for adoption.
It really is. Another is better quantifying and managing the uncertainty in the predictions, knowing how confident the model is. And maybe the most persistent challenge is still the lack of large, representative, publicly available industrial data sets. That holds back progress.
So summing it all up,
Yeah.
what's the big picture here? What should we take away?
I think the core message is that deep learning is fundamentally changing PHM. It's moving us away from just reacting when things break, towards a genuinely predictive approach, anticipating failures, preventing them, with potentially much greater accuracy than before. It's a paradigm shift.
A real shift from reactive to proactive.
Exactly, and it really highlights how knowledge becomes powerful when it's understood and applied effectively. It makes you think, As AI gets better and better at predicting these complex system behaviors, how does human expertise need to evolve? How do we best collaborate with these intelligent systems to achieve even more?
That's a fascinating question to leave us with. How humans and AI collaborate in this space going forward. Well, thank you for joining us on this deep dive into the really revolutionary world of deep learning in PHM. Keep exploring.